All right, picking up where we left off, this is number 15. We want to evaluate the line integral of x cubed z ds, where c is the curve given, again, parametrically. We have 2 sine ti plus tj plus 2 cosine tk for t between 0 and pi over 2. Okay, so again, this might be a little different than the usual line integrals because it's usually some vector field dot dr, right? But this is a scalar field ds. So remember what s is, right? S is the arc length, which is given by this integral here. Usually a definite integral, right, from a to b. So ds then is just the norm of r prime dt, right? So we know what r is. This is r up here. So we do need r prime, the derivative of r. And that's just going to be 2 times cosine of t times I plus 1 times j, and then negative 2 times sine of t times k. And t still goes from 0 to pi over 2. But we need ds, right? ds is going to be the magnitude or the norm of this vector. So it's the square root of, let's see, 4 cosine squared t plus 1 squared plus 4 sine squared t times dt, all under the square root, right? And this is just going to be, well, 4 cosine squared plus sine squared is just 4, so 4 plus 1 is 5. So square root of 5 times dt, right? So that's ds here, right? ds is just the square root of 5 times dt. All right, good enough. So the line integral then is going to be from 0 to pi over 2, that's for t. X, well, x is just the I component, right? The x component, 2 sine t to the third power, and then z is 2 times cosine t, and then ds is the square root of 5 times dt. Okay, so what are we integrating? We're integrating sine cubed of t times cosine of t, and I know I'm missing a number of factors here. We have 2 cubed, right, times 2 times square root of 5. But this is all just a constant. It can come outside, right? So 8 times 2 is 16. We have 16 square root of 5. And then we're integrating sine cubed t cosine t dt. Okay, so this is nothing fancy here. This is just a usual substitution. U will be sine, and the derivative of sine is cosine. So this is my du. And this will just be u to the third, right? U cubed. So we have 16 square root of 5 times the integral of u cubed du. And what about the limit? So when t is 0, sine of 0 is still 0. So the lower limit is 0 here, sorry. And sine of pi over 2 is 1. So we're just integrating from u equals 1, from u equals 0 to u equals 1. Right. So when you integrate, you just get 1/4 u to the 4th from, 0 to 1. So it's just 1/4, right? So 16 square root of 5 over 4. You just get 4 times the square root of 5. And so that's the value of this line integral in the question, right? 4 times the square root of 5. Okay, number 16 is another line integral. Here we're integrating e to the x plus xy dx plus x plus y to the 5th sine of y squared dy. Okay, so yeah, this is in differential form. For those of you that would rather have the vector form f dot dr, you can do that, right? In this case, f is just the vector field whose x component is e to the x plus xy. And the y component is x plus y to the fifth plus sine of y squared. Right? And r, of course, is, well, r is the curve parametrically. So this is a rectangle. I already drew the rectangle here on the right, and we're going counterclockwise. We have the four corners, the four vertices. So if we want to parameterize it, and I don't think we do, this would be a piecewise smooth curve. So we'd need 4 parameterizations here, 1 for each line segment. Okay. Again, probably not that bad because they are just lines. You know, it's easy to parameterize a line. But, you know, we've been through this, and getting the, getting the limits right and matching everything up is not altogether that easy. So I'm hoping there's an easier way to do it than to have to parameterize this. Right. And the thing to note here is that this is a closed curve, right? It closes in on itself. Like that. Oops, I missed. Well, you get the idea, right? It's a closed curve, right? And this vector field here, we should always check if it's conservative. Now, we haven't been doing that because, well, we've been evaluating them directly. I think the last 2 problems, the vector fields were not conservative here, right? But in this case, right, so our m is e to the x plus xy, and our n is x plus y to the fifth plus sine of y squared. So to check if it's conservative, we take the partial of n with respect to x, right, or n sub x, and that's just, well, that's just 1, right? And then the partial of m with respect to y is going to be x. Oops, so my, right? So no, they're not equal. So this is definitely not conservative, because x does not equal 1. Right? I mean, it might at 2 particular points, but not along the entire curve. So, okay, so it's not conservative, right? On the other hand, because it's a closed curve, we can apply Green's theorem. Very useful, even when the vector field is not conservative. Actually, you know, if the vector field was conservative, then there's nothing to do here. The answer would be 0, right? When you integrate a conservative vector field along a closed curve, yep, you're just going to get 0. But since it's not conservative, and we just showed that, you probably won't get 0, although you might. If you do get 0, then it's just a coincidence. You know? Yeah, so Green's theorem just states the following, right? When you're integrating a vector field along a closed curve, and let me go back to the differential form here, right? m dx plus n dy. That this is just the double integral over the region R enclosed by the curve. So what is R here? R is everything inside, right? Everything inside the rectangle. So this region in here, if you will. Right. Okay. So what are we integrating, though? We're integrating partial of n with respect to x minus the partial of m with respect to y over the region R, right? And again, if the vector field was conservative, then this would just be 0, and you'd be integrating 0, which is what would give you 0, right? But in this case, we're actually going to be integrating, let's see, 1 minus x. So let's do dy dx, right? If you want to do dx dy, that's fine too. Y goes from 0 to 4. Right? That's the height of the rectangle. And the width is 2, so x goes from 0 to 2. So I think you can handle this. Again, just treat one at a time. Do the inside integral first. We'll do the outer one later. So when you integrate 1 minus x times y, you just get y minus xy, evaluated between y equals 0 and y equals 4. So this is 4 minus 4x minus 0 minus 0x. Of course, that's just 0. So yeah, we're just integrating 4 minus 4x here from 0 to 2. So that's just 4x minus 2x squared, evaluated between 0 and 2. So 4 times 2 minus 2 times 2 squared. And of course, when you plug in 0, you just get 0. So this is 8 minus 8. So yeah, we do get 0. And as I said, that's a coincidence, right? Even though this is not a conservative vector field, in some cases, you do get 0. So the line integral here, after all that work, should just be 0. Number 17, we're given yet another vector field. This is also a vector field in the plane. And we want to calculate the line integral. But we're given 3 separate curves, right? In part A, we're given the curve, which is the straight line from 0, 0 to 1, 2. So that's just y equals 2x, right? In part B, we're given the curve y equals 2x squared. And in part C, we're given y equals the square root of 4x. Well, I wrote it as y equals 2 squared of x, same thing. And we want to evaluate, right, the vector field, the same vector field, but over each of these 3 curves. Right? And so, essentially, you can parameterize them each pretty simply. I mean, you're given the formulas, so finding the corresponding parameterization, you can, for all 3 of these, you can just use x equals t, and then just go from 0 to 1. Okay, but then you're evaluating 3 separate line integrals, kind of a nuisance, right? So, as I mentioned in number 16, let's look at the vector field here carefully, right? So m is just x squared plus 3y cosine of x, and n is 3 sine of x plus y. So is this vector field conservative, right? Is the differential form exact? So let's check, right? Let's calculate nx, that's the partial of n with respect to x. That's just 3 cosine x, right? Partial of m with respect to y is 3 cosine x. Well, what do you know? They match, right? So if my equals nx, the differential form is exact, the vector field is conservative. Okay. Now, how does that help? Because these are not closed curves, right? If they were closed curves, the line integral would just be 0. But they're not closed, right? They all start at the same point, 0, 0. And they all end at the same point, 1, 2. Okay. So this is where we can use the fundamental theorem of line integrals. It's just like the fundamental theorem of calculus. It's just a bit more general than that. But the idea is the same, right? The line integral of the vector field f, right? It's just going to be the value of the potential function at the final point, which is 1, 2, minus the value of the potential function at the initial point, which is 0, 0. Right? So, well, we need to find the potential function, right? We need to find little f. Right? So remember how to do it. You just have to integrate m with respect to x or n with respect to y. And you get the same thing for both, right? So let's see. Let's integrate m. M was what? M was x squared plus 3y cosine x. Integrate that with respect to x. We're going to get 1/3 x cubed plus, sorry, it's x cubed plus 3y sine x plus possibly some function of y, because when we take the partial derivative with respect to x, whatever this is, it's going to be 0, right? Okay. And we have to get the same thing if we integrate with respect to y. So integrating n with respect to y, n was 3 sine x plus y. We're going to get 3y sine x plus 1/2 y squared plus, again, not a constant, but any function of x, so that when we take the y partial derivative of that, we would just get 0. Right? So putting them both together, what do you notice about these two functions? That they're the same, right? You have the 3y sine x. So that's part of the, that's going to be a term of the potential function, 3y sine x. But what about this 1/3 x cubed? I don't see that in the bottom one. So that has to be the g2 of x, right? It's a, right, 1/3 x cubed is only a function of x. And so my g2 can be 1/3 x cubed, right? Matches perfectly. What about 1/2 y squared? I don't see that in the first version, but this is g1 of y. It's a function of only y. So my g1 of y has to be 1/2 y squared. Okay, so you just add them all up then, right? This is 3y sine x plus 1/3 x cubed plus 1/2 y squared. Oh, I'm forgetting the constant c. Oh, I don't want to use c because c is for curved here, right? So how about k? Okay. So that's the potential function, right? They're all defined up to k. So yeah, there should always be a plus k here, plus k here. Or, you know, these are also plus k. So the g1 and g2, right? Okay, so that's my potential function. Now all I need to do is plug in the initial point and the final point, right? 0, 0, and 1, 2. So let's do that down here. Right? So again, by the fundamental theorem of line integrals, it's essentially the fundamental theorem of calculus, we're evaluating an integral by taking its antiderivative, right? We think of the potential function as a kind of antiderivative, right? I mean, here the derivative is the gradient, right, to give us the vector field. So to undo the gradient to find f is to essentially do this, right, integrate. All right, so yeah, f of 1, 2 minus f of 0, 0. So when x is 1 and y is 2, we get 3 times 2 times the sine of 1 plus 1/3 times 1 cubed plus 1/3 times 2 squared plus k, but that's going to subtract out here, right? So what happens when we plug in 0, 0? Well, we get 3 times 0 times sine of 0, which is 0, plus 1/3 of 0, plus 1/2 of 0 squared, plus k, right? So this is really just going to be 6 times the sine of 1 plus 1/3 plus, oh, sorry, this is 1/2 2 squared. So half of 4 is 2. So this is 6 times the sine of 1 plus 1/3 plus 6/3 is 7/3. Okay, so that's the value of this line integral, 6 sine 1 plus 7/3. Sorry, that's a 6. So that's the answer to all three parts. Part A, B, and C all have the same answer. And again, this was possible only because the vector field was conservative. If the vector field was not conservative, well, then you're out of luck. Then you actually have to evaluate, right, all three of these. You have to parameterize each of them and evaluate each of them separately, and that would take a lot longer than this. But luckily, since the vector field was conservative, we can do this little shortcut here. If we did evaluate each of these separately, it's probably a lot more work, but you would get the same answer for all three, A, B, and C. Oh, if you're worried about the sine of 1, remember that's not the sine of 1 degree, it's the sine of 1 radian. Yeah, the sine of 1 radian is approximately, I think, 0.8415. So 6 times that plus 7 over 3, I think is about 7 point something, 7.3822. So approximately this is 7.3822. So for you engineers out there, yeah, you're welcome to approximate, but again, I was looking for the exact value here. Okay, so yeah, always check if your vector field is conservative. If it is, you're saving yourself a lot of work. And if it's not, well, at least you tried. And you know, if it's not conservative, then unfortunately in this case you got to do it the long way, right? Because you know, you can't use Green's theorem here because it's not a closed curve, right? It doesn't bound a region, right? Like in the last problem, it was a rectangle, right? That bounds a region. When you just have a curve like this, right? There's no region, there's no R, right? Unless the curve, you know, closes in on itself like this, right? Then it bounds a region. But these are not closed curves, so yeah, so it's not going to work out. All right, number 18. No surprise, it's yet another line integral. So here we're integrating the vector field f, and it's given as 3x squared plus yz times I plus xz plus 2z cubed times j plus 2x squared z plus 3yz squared times k. Right. So this is a vector field in space, right? Up until now, I think we've been dealing with vector fields in the xy plane. Okay, so this is a little bit different. And c is given parametrically by the vector valued function. You have t squared I plus t cubed j plus tk from 0 to 1. So this is some curve going from, right, the origin 0, 0, 0, right, to the point, let's say 1, 1, 1, and it's just some curve, yeah, something like this. Gosh, it's hard for me to draw this. There we go, right? So that's some curve C. So you can see it's not a closed curve, right? It doesn't close in on itself. The initial point and the final point are not the same point. Okay. So, but if the vector field is conservative, we can just find the potential function and then evaluate it at these two endpoints, right? The 0, 0, 0 and 1, 1, 1. So, right, so how can we tell if a vector field in space is conservative? So M, N, and P. So for that, you need to take the curl of F. Remember the curl? It's this del operator cross F. So as a determinant, we have I, J, and K, so to get a vector. And then this del is just the three partial derivatives, right? Partial with respect to x, partial with respect to y, partial with respect to z. Yeah. So it's not really a vector, right? I mean, it has three components, but the three components are just these partial derivative symbols, right? They're the partial derivative operators, right? Okay, and then m is just the x component, right? 3x squared plus yz. I got to write small to squeeze it in here. N is xz plus 2z cubed. And p, the z component, is 2x squared z plus 3yz squared. Okay, so the I component will be this determinant. So that's going to be the partial of this with respect to y minus the partial of this with respect to z. Well, maybe I'll write it out, right? So the partial with respect to y of p, which is 2x squared z plus 3yz squared. And then plus j. Now, for a plus j, remember you're going this way, because ordinarily it's minus j. So we're going to do the z partial first, because we're just going to subtract in the opposite order here. So 3x squared plus yz with respect to z, and then minus the x partial of p, which is 2x squared z plus 3yz squared. And I'm going to run out of space here, so I'm going to put plus k on the next line. And this will be this determinant here in the usual order. So the x partial of n with respect, right, well, the x partial of n, right? So xz plus 2z cubed minus the y partial of m, which is 3x squared plus yz. So I sure hope that this is all just 0. Doesn't look like it. Wait a minute. I think I'm missing something here for the first one. I forgot to subtract the z partial of xz plus 2z cubed. Sorry about that. So I got to squeeze that in there. All right. So the I component will be what? It's just going to be 3z squared minus x plus 6z. So this is definitely not 0. So I think we can stop right there. The curl is not the 0 vector, so f is not conservative. So we cannot use the fundamental theorem of line integrals like we did in the last problem. All right, well then how do we evaluate the line integral? Yeah, got to do it directly. Just the direct line integral, right? And we've done several of those earlier, so this is just one more. Gosh, I ruined all this space already. So let me erase all this because we know the curl is not 0. So yeah, so I just got rid of all that. There was no need to do that anyways. Right. All right, so let's just do this directly then. We're doing the line integral of f dot dr. So we need f in terms of t, and, well, we need r prime, right? Dr is just r prime dt. So that's the vector. Oh, this shouldn't be hard, right? This is 2t, 3t squared, and 1 times dt. Okay. The next part is to write f as a function of t. And again, this is a really long thing here, but all I'm doing now is substituting wherever I see an x, t squared. Wherever I see a y, it's t cubed. And wherever I see a z, it's just t. Okay, so 3x squared is 3t squared squared plus yz, so t cubed times t. That's the first component. The second component is x times z, so t squared times t plus 2 times z cubed, so that's just 2 times t cubed. And then 2x squared, so again t squared squared, times z, which is t, plus 3yz squared. So y is t cubed, and then z squared is, well, t squared. So kind of a mess, but notice this is really just going to be 3t to the fourth plus t to the fourth is 4t to the fourth. Here we have t cubed plus 2t cubed is 3t cubed. And then here we have 2t to the fifth plus 3t to the fifth is, sorry, it's supposed to be a 5t to the power 5. So that's a nice coincidence that the coefficient is the same as the exponent. right? So this is the vector function that we're integrating, with respect to t. So now f dot dr is just, well, this vector field, right, dot product with dr, which is 2t, 3t squared 1 dt. So 4t to the 4th times 2t is 8t to the 5 plus 3t cubed times 3t squared is 9t to the 5 plus 5t to the 5 times 1, that's just 5t to the 5. Well, oh, times dt. Don't forget the dt here. Well, 8 plus 9 is 17. 17 plus 5 is 22. So this is 22t to the 5th times dt. So we're integrating that from t equals 0 to t equals 1. Again, that was given in the problem, right? So, yep, the line integral after all that is just the definite integral from 0 to 1 of the function 22t to the 5th. So 22 over 6, t to the 6 from 0 to 1. 22 over 6 is 11 over 3. Okay, so yeah, it looked like this was going to be pretty horrible, but it simplified quite nicely. And so even though this was a direct calculation, you get a pretty nice answer, relatively speaking, and you get a very easy integral, right? It's nothing fancy here, no by parts, no trig substitution, no regular substitution. It's just worked out very nicely. So apologies that I wasted all that time trying to determine if f is conservative. It wasn't, and it doesn't matter. The direct integral, the direct line integral here was easy enough, I think. All right, so let's go on to number 19. All right, number 19. Looks like we're done with line integrals for the time being. So they just give us a scalar function. F of x, y, and z is just x squared yz. And part A, they just want us to calculate the gradient. So I think you can practically do that in your sleep, right? Remember, the gradient is just the vector whose components are the three partial derivatives. So f with respect to x, f with respect to y, f with respect to z. And each of these are pretty simple, right? With respect to x, you get 2xyz. With respect to y, you're going to get x squared times z. And with respect to z, you take the derivative, you just get x squared y. Yep, so you can write it like this, or if you prefer the linear combination of I, j, and k, it's just 2xyz times I plus x squared z times j plus x squared y times k. And again, I am not picky how I want the answer here. All right, simple enough, right? Part B, it looks like we're going to take the dot product of del and the gradient. Right. It turns out this is actually a rather important operation. It's sometimes simplified as just del squared f, and this is called the Laplacian. Okay, so it's not something you're probably going to see very much unless you take, a course in, say, partial differential equations or electromagnetism. So in more advanced math and physics courses, this is a very important operation. So what do we mean by the dot product, right? We really mean just take the divergence of the gradient of f, right? So we already took the gradient. That was in part A. Now we just need to take the divergence of that, right? So it's essentially just the partial with respect to x of the x component, 2xyz, right, plus the y partial derivative of, right, of n, the y component, x squared z, and then plus the z partial of x squared y. Okay, yeah, be careful. It's a dot product, so it's a scalar. It's not a vector. There's no I, j, and k here. If you put I, j, and k, it's wrong. Okay, it's not a vector. It's a scalar. And in fact, it's a very simple one, right? The partial with respect to x of 2xyz is just 2yz. And then these partial derivatives are just 0. So this is just 2yz. Okay. And finally, part C is the curl of the gradient, right? So this, when you take the cross product, remember that means it's the curl. So, yep, we can think of this as the curl of the gradient of f. Right. And again, we did the gradient in part A, so we just need to find the curl of that vector field. So the curl of, I'll call it capital F. So this is my capital F. Right. So I'm going to do the usual determinant, I, j, and k. And these are the partial derivatives. And then the three components are 2xyz, x squared z, and x squared y. Okay. So for the I component, we take this determinant. And I'm not going to write it out this time. I think we can do this in our heads, right? The partial of x squared y with respect to y is just x squared. And then the z partial of x squared z is x squared. So that's the I component, right? Plus the j component will be the z partial of this, right? So 2xy minus the x partial of this. So the derivative with respect to x of x squared y is, yep, 2xy. So this is looking good, right? This is just 0i plus 0j. But hang on, we've got to do the z component. So that's going to be this determinant here. So the x partial of x squared z is 2xz. And then minus the y partial of 2xyz is 2xz. Yep, so that's 0 as well. So 0i plus 0j plus 0k is the 0 vector. Remember, when you take the curl of a vector field, you get a vector, right? It's the 0 vector field, but it's the 0 vector. So again, if you just write 0 without an arrow over it, that's wrong. The 0 vector is not the same as the 0 scalar. Okay, so, all right. And in fact, well, it turns out you're always going to get 0 here. It doesn't matter what the function is, right? And I would advise you to prove this, right? For any function, take the gradient of it and then take the curl of that. It turns out you always get the 0 vector. So, of course, it's going to work for this particular function, but it doesn't matter. It could work for any function, any scalar function here, right? All right, so that's number 19. Let's go on to number 20. Okay, so now we're given a vector field, right, with three components. So this is a vector field in space. And part A, we just want to calculate del dot f. Also known as the divergence of f. Okay, so as before, we take the partial derivative with respect to x of m, that's x squared plus y, plus the y partial of yz, plus the z partial of xy. Again, no vectors here, no I, j, and k. This is a scalar function now. So what do we get? 2x plus z plus 0. Yep, so just 2x plus z. Right, so it's not a vector, right? It's a scalar function, right? So you can think of this as like a little f. Oh, well, okay. Maybe not, right? Little g. Because I don't want to give you the impression that, right, this is a vector field, maybe it's conservative, and then maybe this is the potential function. It's not. It's not. Yeah, I don't even think this vector field is conservative. I'd be surprised if it was. So let's just say this vector field is not conservative. Okay. All right. Part B, we take the curl, right? So del cross F, also known as the curl of F. Right. We've done this before. Again, I like using the determinant because I can never remember the formula just by looking at all the subtractions, what goes where. So yeah, m is x squared plus y. Oops. N is yz, and p is xy. So again, without writing it all out here, this determinant is just the y partial of xy, which is just x, minus the z partial of yz, which is y. And then, oops, I messed that up. Get rid of that. So, oh, but I wanted to keep the determinant here. So now the j component or the y component will be, see, 0 minus y. And then the k component or the z component will be 0 minus 1. So I think we just get the vector x minus y, negative 1. Or, yep, if you want to leave it in terms of I, j, and k, x minus y times I, minus y times j, minus k. So, yeah, not picky about that. Okay. Part C now is this weird thing. It's basically, like a second derivative. It's del of the divergence. So we already calculated this thing. This is the divergence. In fact, I called it little g here. Right. So what are we doing? We're just taking the gradient of this little g. Right? G is 2x plus z. Right? So 2x plus z. So the gradient of that should be very easy. You take the x partial derivative, you just get 2. The y partial derivative is 0, and the z partial derivative is 1. So in fact, you just get a constant vector, 2, 0, 1. Or if you prefer, 2i plus k. Okay. So yes, this is the gradient of the divergence, right? You can take the gradient of the divergence because the divergence of a vector field is a scalar function, and you can take the gradient of a scalar function. In this case, you just get a vector field. Well, it's a constant vector field, right? So think about this vector. This same vector is pointing everywhere in space. No matter where you are, same vector everywhere, right? Okay, and then part D is the divergence of the curl. So this, right, del dot means we're taking the divergence of the curl. Divergence of the curl. Right, and we already took the curl. That was part B. So we're just really taking the divergence of the vector field, right, x minus y, negative 1. And that's pretty easy. Just take the x partial derivative of x minus y plus the y partial derivative of negative y plus the z partial derivative of negative 1. So with respect to x, you just get 1 minus 0. With respect to y of negative y, you just get negative 1. And the derivative of negative 1 is 0. So 1 minus 1 is 0. Right? As a number, right? It's not a vector. It's a number. Right? Divergence is a dot product, right? So scalar should be your answer, right? Now, in general, you'll get a scalar field, right, like 2x plus z or something. But it turns out that anytime you take the divergence of the curl of any vector field, you will always get 0. In fact, this was a theorem. I don't know if I proved it or not. Back in 15.1, I believe. It was somewhere in chapter 15, I think. Yep. The divergence of the curl of any vector field is just 0. Oh, not any vector field, right? There's a condition on this. It has to be a nice vector field. What do I mean by nice? Well, it has to be differentiable, right? Certainly has to be continuous, differentiable, and twice differentiable. So I think the second partial derivatives have to be continuous. So second partials have to be continuous. Right. Yeah, in math we give, right, because we do this a lot, rather than write out all these words, even the abbreviations, we just say it's a C2 function. So a C2, a C2 vector field, I should say, is one where the second partial derivatives are all continuous. And that's certainly the case here, right? We can certainly take the second partial derivatives of all these components, and they're nice differentiable continuous functions. So number 21, let G be the vector field x squared y times I plus y squared, y z squared times j plus y squared z times k. Okay, so I write it in component form, but I just rewrote it in the I, j, and k form. So the question is G conservative? And if it is, find a potential function. So is G conservative? Yes or no? I mean, we could just guess, but, you know, if we guess no and it is, then we're missing the potential function. So if it is conservative, we can find a potential function, which we'll appropriately called G, little g of x, y, and z. All right. So is G conservative? Take the curl. If the curl is the 0 vector, then the answer is yes. If the curl is anything other than the 0 vector, then the answer is no. All right. So we'll just do this the usual way. I, j, and k, partial derivatives. And then the components, x squared y, yz squared, and y squared z. So the curl of G is, so the I component will be 2yz minus 2yz. Okay, so far so good. That's 0. And then the j component will be, let's see, 0 minus 0. So that's good. And then the k component will be 0 minus x squared. Right? So the partial of this with respect to x is 0. And then the partial of this with respect to y is x squared. So unfortunately, right, the answer here is no. It's 0i plus 0j, but it's minus x squared k, or just negative x squared k. You can leave it like that. But if you're writing it out in its component form, you have to put 0, 0, negative x squared. Oops, like that, x squared. Perfect. All right. Well, there we go. So the answer is no. Right? G is not conservative. And so there's no point in finding a potential function. It doesn't have any. Right? It does not have a potential function. Right. What happens if you try to find it? Right? So in other words, if I integrate m with respect to x, and I integrate n with respect to y, and I integrate p with respect to z, I was going to say k, but p dz, you'll find that you cannot possibly make it work, that they don't match, right? So there just won't be a way to equate all these together, right? All right, so 22. essentially the same question, but with a different vector field. So here, this is the vector field F, and it has the usual three components, so it's a vector field in space, and we want to know, is it conservative? So, as always, just take the curl. Right. So, I, j, and k, and then the second row are just the partial derivative symbols. And by the way, when you see this, if that looks confusing, it just means this. You know, that's a kind of a more advanced notation, but eventually this becomes a little bit easier to deal with. So, in fact, let me leave that up. This is just shorthand for the partial with respect to x. Okay. All right, so m is y plus z e to the x, n is x plus y, and p is e to the x minus cosine of z. So let's see what we get. So for the I component, the partial of this with respect to y is 0, because there's no y there, right? And the partial of x plus y with respect to z is also 0. So that's good. Let me erase this line. All right, and now the j component, or the y component, with respect to z, this is just e to the x. And then with respect to x, this is e to the x. Okay, so that's 0. But remember in the last problem, if you assume, well, the first two are 0, the last one has to be 0, right? Nope, not necessarily, right? So if you're not careful and you just kind of mess this up, or you assume that this was 0, you would think it's conservative, but, right. So in this case, again, we're taking this determinant here. With respect to x, this is just 1. With respect to y, this is also 1. 1 minus 1 is 0. So all three components are 0, so we do get the 0 vector. So here the answer is yes. F is indeed conservative, which is nice. However, now we have this one extra step, right? We also have to find the potential function. So we have to find little f. Right. And you know why we would have to do that, right? If we're doing a line integral, we can just evaluate the potential function at the two endpoints. Or if it's a closed curve, then you automatically get 0 for the line integral. Right? Okay, so we have to integrate m with respect to x. So that's going to be, let's see, y plus z e to the x dx. So I think we get xy plus z e to the x plus, don't forget, not a constant, but any function. I hate using g here. How about h? Any function of either y or z or both. Right? Okay. And then we integrate n with respect to y. So that's x plus y. With respect to y, we get xy plus 1/2 y squared plus some function, I'll call it h2, of either x or z, or both. And then we have one more integral to do. This is going to be the integral of p with respect to z. I forgot what p was. Oh, e to the x minus cosine z. With respect to z. So the derivative of sine is cosine, so I think we just get negative, or we get, sorry, z e to the x minus sine of z plus some function, say h3, of x and y. So somehow we have to match all these functions here, right? So what could my potential function be? So let's see. We have, well, xy is in both of these, but it's not in the bottom one anywhere, is it? On the other hand, h3 is a function of just x and y. So, right, so that means this thing has to be xy. Yeah. plus 1/2 y squared. Yeah, it has to include that too, right? So xy plus 1/2 y squared. It's the whole thing. Right. So that's just a function of x and y. Okay, so xy plus 1/2 y squared. Okay, anything else? So how about z e to the x? Z e to the x? Well, it's a function of just x and z. So my h2 has to be z e to the x. Oh, and I think we also want to include the sine of z, minus the sine of z here. Shoot. So, yeah. Z e to the x minus sine z. Great. So I think that's everything we need. What about this function of y and z? Well, that has to include the 1/2 y squared minus sine of z. So this is just 1/2 y squared minus the sine of z. Right, because that was not included in the first two terms here. So I think that's everything. Again, don't forget your constant k. You can use c in this case because there's no curve here. So, yep, we took the curl, we got 0, the 0 vector, so we knew it's conservative, so we know there has to be a potential function, and this is it right here. That's our potential function. Right. And so that's it for number 22. Okay, number 23, we want to find the surface area of the surface z equals y squared minus x squared. So I'm just giving that a name. I'm calling it a little f, right? Between the cylinders, x squared plus y squared equals 1 and x squared plus y squared equals 4. So succinctly, you can just write x squared plus y squared between 1 and 4. Now remember, x squared plus y squared is just r squared. And when you take the square root, and r is positive, right, you're just getting two circles, one with radius 1 and one with radius 2. So you get this little ring we call an annulus. So that's it. Let me draw the x and y axes too, because this is centered appropriately here. Okay, so that's x, that's y. So, yep, we're between radius 1 and 2. So this is not to scale, but yeah, 1 and 2. Close enough. Okay, so that's my r here, if you like. And so there's a lot of ways you can calculate surface area. The old-fashioned way from chapter 14 is just to do a double integral over r. Well, yeah, officially it's the surface S, ds. But to evaluate that, you're doing the double integral over r of the quantity ds, which is the square root of 1 plus partial of f with respect to x squared plus partial of f with respect to y squared. dA, right? Where a is it's the area of this little ring here, right? Yep. So again, this is on your formula sheet if you forget it. So we need the partial derivatives. What are the two partial derivatives? Fx is just negative 2x. Fy is just 2y. So when you square them, you get 4x squared and 4y squared. So this integral here, the integrand is just 1 plus 4x squared plus 4y squared. And then dA, well, dy dx. But I hope you're not going to do this in rectangular coordinates because these are, disks, circular regions. So I would highly recommend switching to polar coordinates, r dr d theta. right? So r goes from 1 to 2. That was given. And theta, well, we want to go all the way around, right? So 0 to 2 pi. Right. Now the integrand is going to be 1 plus 4, right? X squared plus y squared is r squared. And again, if you think this is a tricky integral, remember you have this extra r here from the Jacobian, right? dy dx is r dr d theta. So, yep, so we can just do an ordinary substitution. U is 1 plus 4r squared. Du will be 8r dr. So we need an 8 here, and then just divide by 8 on the outside. So 1 over 8, integral from 0 to 2 pi, which we could do separately, but we'll do later. So then we're just going to integrate the square root of, the square root of u du. And then we'll do the theta, right? So this is only for r. So if r is 1, u will be 1 plus 4 times 1 squared. 1 plus 4 is 5. And if r is 2, then u is going to be 1 plus 4 times 2 squared. That's 1 plus 4 times 4. 1 plus 16 is 17. So u goes from 5 to 17. And I put this off long enough, but there's no theta here. So with respect to theta, this just becomes the usual 2 pi. But this integral here, yep, we have to do that. So the integral of the square root of u to the 1/2, is 2/3 u to the 3/2. And then we just plug in the 5 and the 17. So remember, u to the 3/2 is just u squared of u. So this will be 17 square root of 17 minus 5 square root of 5. Right, so 1 over 8 times 2 over 3 is just 1 over 12. So this will be 2 pi over 12. So this will be pi over 6 times 17 root 17 minus 5 root 5, whatever that is. Okay. So that's the exact answer. You can always approximate it if you want. But that's the exact surface area of this surface. What is this surface? Again, I'm not asking that. And you can see I'm not graphing the surface, right? I'm graphing the region R over which there's this surface. This is a hyperbolic paraboloid, also known as a saddle, right? Which is why I'm not going to draw it, right? It's this kind of a thing here. It goes up one way, down the other way. Yeah, I can't draw it. So, oh, I know. I'm drawing it upside down. It looks like this. Right. Yeah. Anyways, yeah. So that's the basic graph of it. So yeah, it's the surface area will just end up being this. All right, 24. All right, number 24, we have a surface S given parametrically. So this is R as a function of u and v. So u and v are the parameters. And the vector field is just uvi plus u plus vj plus vk. And we're given the bounds on u and v. U just goes from 0 to 2, and v just goes from 0 to 3. So in the uv plane, right, this is just a rectangle of height 3 and width 2. So this is what I'm calling D here. It's just this rectangle here. All right, we're given a vector field in space, right? xi plus 3zj plus 2yk. And so our goal is to evaluate this surface integral. Okay, so we've been doing a lot of line integrals. Now we're doing a surface integral, right? And I don't know what this surface is, right? It's just some surface sitting in space. this. Right? Who knows what it really looks like? So that's some surface S, right? And, right, you have a vector field along the surface, so some vectors are pointing this way, some might be pointing downward, you know. It's some vector field. Some may be tangent to the surface, but probably most of them are pointing either upward or downward, or inward or outward, however you want to describe it. Yep, so we want to calculate the total flux integral here. How much of the vector field is passing through the surface, and how much of the vector field is just, you know, if the vector field is just going across the surface, then we know the flux is 0. Right. So, right. Oh, and the flux could be 0 in the case that you have a positive vector field above and negative below, and they could end up canceling each other out. So that's another possibility. It doesn't mean that there's no vector flowing through the surface. It just means that some are flowing one way and some are flowing the other way. Right? And in the end, you could get 0. I don't think we're going to get 0 here. I'd be shocked, but it's possible. Yeah, so how do we evaluate this surface integral? So we have f, but right, we're probably going to need f in terms of not x, y, and z, but in terms of u and v. Right? So x is just u times v. Right? 3 times z is just 3 times v. And 2 times y is 2 times u plus v. Or maybe better yet, 2u plus 2v. Okay, so, right, what we're doing here is we're essentially confining the vector field to the surface, right? Right, this here is a vector field everywhere in space. So even though the surface is here, there are vectors that are not attached to the surface, that have nothing to do with the surface. But by replacing x, y, and z with the corresponding, you know, functions of u and v, we're not worried about these vectors anymore. We're only worried about the vectors confined to the surface. Does that make sense? Okay. What else do we need? We need the vector n, right? Remember, n stands for normal vector, right? And this could also be a function of u and v, right? Different places along the surface have different normal vectors. Right? So how do we find that? Well, in terms of u and v, right, this is going to be r, the partial of r with respect to u, cross the partial of r with respect to v. And this may be a unit vector, but probably not. So that means we have to normalize it. Actually, if I remember right, I don't think we have to do that, because that will be sort of incorporated in the ds part. In other words, right, the nds, right, will just be this in terms of u and v. Right, so that comes later. Let's just do ru cross rv. So we have, it's a cross product, right? So ij and k, the partial of r with respect to u, oh, let's write it out. Partial of r with respect to u. So that's partial of x with respect to u, partial of y with respect to u, partial of z with respect to u. And then the last row is partial of x with respect to v, partial of y with respect to v, and partial of z with respect to v. All right. So that's, yeah, that's just the cross product. Now we can do this. Let's write it out specifically. Right. So, so this is my x, this is my y, this is my z. So partial of x with respect to u is just v. Partial of y with respect to u is just 1. Partial of z with respect to u is 0, right? Because v is z. So the partial of v with respect to u is 0. Right? Partial of x with respect to v is u, partial of y with respect to v is 1, and partial of v with respect to v is also 1. So, right, so now just taking the cross product, we're going to get I minus v times j, and then v minus u times k. Right? So that's my n. You can think of it as just 1 negative v, v minus u. Okay. Yep. So now all we need to do is integrate over the surface S, well, over the rectangle. I don't know why I'm calling it D again. It should be R for rectangle here. But here I'm using D, right? Again, f dot n ds, which in this case is what was, here I'll make a little more space for the bounds. F is the vector field uv, 3v, 2u plus 2v. And n is the vector field that we just found is just 1 negative v, oops, and then v minus u. And right, we're just integrating du dv or dv du. U goes from 0 to 2, and v goes from 0 to 3. Right, so before we integrate, I guess we need to actually calculate this dot product. It's just going to be uv, and then minus 3v squared, and then, so, all right, let's try this. So this is 2 u plus v times, or v plus u times v minus u. Right, so 2 times v squared minus u squared. So plus 2v squared minus 2u squared. Right, du dv. Oh, and negative 3v squared plus 2v squared is just negative v squared. So, yep, let's simplify first. Oops, minus 2u squared. Okay, so this should not be hard. We'll do the inside integral first. Yep, with respect to u, so we're going to get 1/2 u squared v minus uv squared minus 2/3 u cubed, and we're evaluating u between 0 and 2. Okay, so that's going to be 2v minus 2v squared, and then, yep, u, so 2 cubed, 16 over 3, minus 16 over 3, I think, dv. So now integrate with all of this with respect to v. Oops, we can do that, I think. So we get v squared minus 2/3 v cubed minus 16 over 3 times v. And now just plug in the 0 and the 3, right? So, yep, when you plug in 0, you get 0. So this is 3 squared minus 2/3 3 cubed minus 16 over 3 times 3. So 9 minus 18 minus 16. So negative 9 minus 16, I'm thinking negative 25. Right. So, yeah, I think the answer is, so what does it mean to be negative? Well, it just means that most of the vector field is flowing against, right, the opposite direction of the normal vector. So, right, so if this is my surface, right, and my normal vector is pointing this way, and I don't remember which way it's pointing, but let's say it's pointing this way, it just means that the net flow of the vector field tends to be pointing in the opposite direction. Okay. So in other words, the dot product would be negative. So that's how you can get a negative flux. Right? So yeah, so the flux integral here, after all this, should just be negative 25. Okay, that brings us to 25. So here we're given yet another vector field. So this is capital F, and it's a vector field in the plane. There's only two components, right? So x minus y squared times I plus x plus y squared times j. And we want to evaluate the line integral over the curve. And this curve is the quarter unit circle traversed clockwise. So, yep, it's given in this picture over here. You can see the picture. Right? So this is a closed curve, right? It's not just the circle part, but it's, right, this circle going, or quarter circle, I should say, going counterclockwise, and then going down, and then going across. So, right, so it's a closed curve here. Sorry that's not clear from the description, but it's clear from the picture, at least I hope so. All right, so, right, so because it's a closed curve, we should be able to apply Green's theorem. Remember Green's theorem, so if this is m and n here, right, and we're just doing a line integral m dx plus n dy, that we can also calculate the double integral over the region R. What is R? R is this region in here, this 1/4 of a disk, essentially. So, yep, but we're integrating the partial of n with respect to x minus the partial of m with respect to y. If you can't remember that, don't worry about it. It's on your formula sheet, right? Yeah, so we just need the two partial derivatives, right? M with respect to y is just negative 2y. N with respect to x is just 1. Is that right? Yeah. So the integrand here, the thing we're integrating, is 1 minus negative 2y, right? Or just 1 plus 2y. We can do dy dx. Although it is a circular region, so I would tend to use polar coordinates here, although you don't have to. But well, I'm going to do it because I find it easier. Right? So this is, instead of 1 plus 2y, it's 1 plus 2 r sine theta. And the dy dx is r dr d theta. So don't forget the extra r. The Jacobian. R just goes from, well, yeah, the radius is 1, right? 1, 0, 0, 1, so 0 to 1. And theta, well, we're going from 0 to pi over 2, right? 0 to pi over 2. That's 1/4 of the circle, right? Yep, we're not going all the way around, so it's not 0 to 2 pi. We're not even going halfway around, so it's not 0 to pi. We're going 1/4. So 1/4, if you like, right, 1/4 of 2 pi is pi over 2. But you should recognize that the positive y-axis is just 90 degrees or pi over 2. All right, so this should not be a difficult integral to evaluate. We'll do the r integral first, as always. Now, this does depend on theta here, so I don't think we can split this up as the product just yet. So, yeah, so we really just will evaluate the theta integral second. So when you integrate with respect to r, yeah, don't forget to distribute the r here. So the integrand is r plus 2r squared sine theta, right? dr d theta. So, right, so when you integrate r, you get 1/2 r squared. Sorry, that does not look right. That looks better. And then plus 2 times 1/3, so 2 over 3 r cubed sine theta. Right, So that's the integral. Now we just evaluate it between r equals 0 and r equals 1. Right, so that's just 1/2 plus 2/3 times sine of theta. Right, minus 0. There, yeah, you plug in 0, you just get 0. So, yep, so now when we integrate this, we just get 1/2 theta minus 2/3 cosine theta. And then we'll just evaluate that between 0 and pi over 2. So we get 1/2 of pi over 2 minus 2/3 of cosine of pi over 2, which is 0, right? Now be careful. When you plug in 0, you get 0 over 2, but then you get minus 2/3 times the cosine of 0. Yep, you don't get 0. Cosine of 0 is 1. So I think we get pi over 4, right, minus 0, and then minus 0 minus 2/3. So we get pi over 4 plus 2/3. Or, if you prefer, right, 3 pi plus 8 all over 12. And that's the line integral. Okay, one more, number 26. All right, so we're calculating yet another flux integral for this vector field, xyi plus yzj minus yzk, over the surface S. Now, S is the hemispherical dome of radius 4. And again, if you don't know what that is, they give that to you, right? It's z equals the square root of 16 minus x squared minus y squared, along with the disk of radius 4 in the xy plane, and that's just z equals 0. Okay, so what they're telling us is that this is the dome part here, right? So that's just this, right? Which would be an open surface, but they're including the floor here. Right? So what that means is this is a closed surface, right? It's a closed dome. Okay. Yeah, and in fact, some books put a little circle through the integral to indicate that it is a closed surface. Here, it's just understood when you read the question carefully, you understand that when they say along with the disk of radius 4, they mean this purple part down here, the flat parts of the dome, right? Okay, the floor, the dome is the ceiling. Okay, yeah, so how can we do this? Well, because it's a closed surface, we should be able to apply the divergence theorem. I mean, we could calculate this directly. That might be a little bit of work. It's probably not hard, but it takes a little more effort. So the divergence theorem says that instead of doing the surface integral, I can just calculate the volume integral, right, dv, but what I have to integrate is the divergence of this vector field. Right, so we're given the vector field. I think we can calculate the divergence pretty easily, right? It's just the partial derivative with respect to x of xy plus the partial derivative with respect to y of yz plus the partial derivative with respect to z of negative yz. So I think we get y plus z minus y. Right? So we just get z. Right? So, yep, we're just integrating z here over this volume. So by volume, right, we mean everything under the dome, but above the xy plane. So everything inside here, right? the solid hemisphere. The solid hemisphere, right? Or if you want to think of it as half of a ball. So that's my Q. So that's just Q here. Right. So I don't think this is all that bad. So we're integrating Z. And this is, I mean, look, this is a half of a sphere. That just cries out for spherical coordinates. So my dV, if you remember, is rho squared sine phi, right? d rho d phi d theta. Let me write it over here, right? Rho squared sine phi d rho d phi d theta. Okay. So all of that is just dV. Right? But yeah, there's a problem. There is no Z in spherical, right? You can use Z for rectangular or for cylindrical, but not for spherical. So remember what Z is in spherical. It's just rho cosine phi. So let me just plug that in here. Let's get rid of the Z and write that as rho cosine phi. Oops. Just to remind you, I'll put the Z up here. But that used to be Z, and then all of this stuff down here is the dV. Okay. So rho times rho squared is rho cubed, and this is sine phi cosine phi, which you could write that as 1/2 sine of 2 phi, but I prefer not to. D rho d phi d theta. So now we just need the bounds. So what are the bounds for rho? Well, let's see. This is radius 4, so we're going from 0 to 4. That's the radius of either the disk or the sphere, right? Phi is the angle with the z-axis. So this is the z-axis. This is the xy plane. This is the projection of it, right? The two-dimensional version. Yeah, so we're only going from 0 to pi over 2, 90 degrees. Right? It's not the full sphere. We're not including the bottom half of the sphere, so we're not going to pi. Right? So it's not 0 to pi. It's certainly not 0 to pi, 0 to 2 pi. Right? It's just 0 to pi over 2, 90 degrees. Right? We're not including the bottom half of the sphere. All right, and theta, well, theta goes all the way around, right? You can see that from the picture up here. If this is the x-axis, we're going all the way around the z-axis here, right? So, yeah, theta goes from 0 to 2 pi. Right. And I think you can take it from here. In fact, these are all separable. You can write it as a product. 0 to 2 pi d theta, 0 to pi over 2 sine phi cosine phi, d phi, and then 0 to 4 for rho cubed. Okay. So the first integral, no surprise, 2 pi. The second integral, well, maybe some of you know this by heart. I don't. I use a substitution. U is sine phi, and then du is cosine phi. So you're just integrating from 0 to 1, u du. So, yep, you should just get 1/2 there. And then the integral of rho cubed is 1/4 rho to the 4th. Between 0 and 4, so that's just 4 to the 4 divided by 4, or 4 to the 3, which is 64. So we get 2 pi times 1/2 times 64. So 64 pi. Right? So I think that looks good. And that should do it. So I hope this helps. you know, it's, so I think I did most of these problems on the practice test. I might have skipped one or two. I know I skipped number 1 because I'm hoping that's too easy. So don't expect questions quite that easy. But yeah, most of these you just have to, you know, the hard part I think is remembering when can you use the divergence theorem, right? When can you use Stokes' theorem? When can you use Green's theorem? And when can you use the fundamental theorem of line integrals, right? So you have to distinguish between, are you integrating a surface or just a curve, right? So is it a line integral or a surface integral? Is the curve open or closed, right? Because if it's an open curve, right, if it doesn't close in on itself, then you can't use Green's theorem. But you might be able to use the fundamental theorem of line integrals if the vector field is conservative, right? Otherwise, you just have to do it directly. If you're talking about a surface, right, if it's an open surface like this, then we would not be able to use the divergence theorem. The divergence theorem only applies to a closed surface, right? Like a sphere is closed, or half of a sphere, if you include the bottom part, right, is closed. A cylinder is closed as well, right? If you include the top surface and the bottom surface, right, the two disks and the side, that's a closed surface as well, right? But, you know, but it depends, right? You can have a cylinder that's open, right? In other words, you just have the side here, and you might have the floor, the bottom of the cylinder, but if the top is open, if there's no lid on the cylinder, then it's an open surface, right? And then you would not be able to use the divergence theorem. Okay, so I hope this helps. So best of luck on the final exam.